Hi, welcome to the second Apex.ai Autoware lesson. I'm Catherine Scott. I'm the developer advocate for Open Robotics. If you're not familiar with Open Robotics, we are the sort of steward organization that helps build ROS and Ignition Gazebo. The hope today is that we'll go through basically a brief tutorial on all of the C++ API functions inside of ROS2. This isn't meant to be exhaustive, but it's basically to give you an introduction to all the building blocks that are used in most ROS systems, and from those building blocks you can build up much more complex systems. So we'll sort of be working systematically through most of the ROS API to build up to more and more complex sort of application development. Today we'll be using ADE, which is the Apex AI sort of Dockerized container version of ROS, and what we'll be doing is installing most of the ROS2 dashing tutorials and working through some of them, and I'll be giving you a few hints and tips and tricks as we go along. If you have any questions, please feel free to let me know. We'll be doing a little bit of work with also the ROS2 sort of CLI interface. The next lesson is actually going to cover that more in detail, so if you miss a few things right now, don't feel like you have to get it all in one go. We'll go through that sort of systematically in the next lesson. Right now, the hope really is to get you familiar with how to build ROS applications, what the sort of primitives are that are used to build systems, and what the API looks like. And then sort of next time we'll go through how to run things, how to deploy things, how to debug them, and give you a good sense of just how to paw around in a ROS system and see what's going on and look at the goo inside. Let's see. So I've also taken a lot of time and built this lesson out as a restructured text document that auto-generates slides. So there's both HTML slides and PDF slides. So you can either follow along on those, or you can actually look at the restructured text document itself and follow along either as we go, or sort of watch the lecture and then go through and try it all out yourself. I would recommend getting AD installed before we begin. So that should help you get started. To answer the question I get on all of my Zoom calls, yes, that's a VT100 behind me. It actually came from Carnegie Mellon University as property dispo. It was from the psych department, so it's been rebadged and it was used for psychological tests way back when. Okay, so give me a second to switch over and we'll start going through some of this code and I'll give you an idea of what's going on. All right, so I've got everything queued up here, and what you can see basically is on the left I have my HTML slides, on the right I have a Ubuntu terminal and a little bit of video, and we can basically get started and start talking about the ROS2 API and some of the build tools. All right, so why don't we get started? I think we got to preface all of this by saying this lesson is intended to be basically a crash course in ROS2 dashing and its API and maybe a little bit of the build tools. And the hope is that after this lesson you should be able to code and build basically a rudimentary ROS2 application. You may not get all of it, but you'll understand the basics and how things are sort of put together. It should be noted that since this is a crash course, we're giving you a pre-configured Docker environment called ADE. We're not going to cover sort of all of the logistics of setting that up. This is basically an exercise you're going to have to cover. I've tried to structure this all to work off the ROS2 dashing desktop installation. So if you're on Ubuntu or you can get an Ubuntu VM, you should just be able to apt-get install it and get going. It also should be noted that right now this crash course was written for ROS2 dashing. ROS2 Foxy is going to be released in a couple weeks, and Foxy is going to be a big, major, stable LTS ROS release. So you're going to learn all this in dashing. Things have changed a little bit in Foxy. As soon as you feel like you're capable of it, I would highly recommend switching over because you'll just get better support. It's sort of the ROS2 version that we hope to be supporting for a long time. The other thing that I'd like to say up front is that the next lesson will cover basically the ROS2 CLI interface. So if I run a few commands here and you don't get them the first time, or if I don't cover them fully, that's okay. So just go ahead and sort of parrot what's going on, and we'll cover it in detail next time. Okay, so the other thing I want to say about ROS is that it's difficult. Like learning these things is going to be hard. This is the only image I have. It's sort of one of these, we choose to go to the moon, not because it's easy, because it's hard. We choose to learn how to do robotics, not because it's like easy web dev. We choose to do it because it's hard and it's interesting. And I want to say that, you know, in this process, you'll almost certainly get stuck. You'll certainly not understand something fully. You're going to need help. Everyone needs help in learning ROS. That's just sort of the nature of the animal. We're doing hard, difficult things that are changing all the time. And so I wanted to make sure before we even began to sort of look at some of the resources that are out there, that when you do get stuck, don't get frustrated. There's help out there. So why don't we start? So we have a ton of resources, and you have to understand that ROS has been around for well over a decade. So some of our resources actually even predate what you would kind of consider normal at this point. Why don't we do a quick rundown of what's out there? So the first resource that I would suggest is if you have a general question. ROS, we have our own Q&A site, kind of like Stack Overflow. It's called Answers, so it's answers.ros.org. It actually predates or was built at the same time as Stack Overflow, so you really have like a decade's worth of question and answer content there, and all of the core developers are there. A good chunk of the community is there, so if you have questions, that's probably your first place to go. We also have a discourse server, so it's just discourse.ros.org. This is more sort of community announcements and discussion and news and those sorts of things. The one thing that I ask, because I sort of moderate discourse, is do not ask questions on discourse that should be on answers.ros.org. This is sort of a thing that happens all the time. If you have a very specific question, answers.ros.org is where you're going to get immediate help on that. We also have a very, very large ROS wiki. It's mostly for ROS1, and it's just wiki.ros.org. Most of that content is generally still helpful. It may not be relevant to your particular version, but conceptually, most of the content there is correct. When it comes to ROS2 documentation, it's in a different spot. We're taking a different tact with how we're building it, and you can find that at index.ros.org/docs/ROS2. And so if you're looking for documentation, that's probably the place to go. Most of this tutorial basically pulls directly from that, and so you should be able to find more detailed explanations, sort of follow-on lessons, and additional materials there. While we have a second, there's also sort of unofficial resources, so other places you can look. There is a ROS and robotics subreddit. Those are great places to also have discussions. I prefer you go to sort of the community-sponsored stuff, but those are there. You should know about them. There's also an unofficial ROS Discord server that you can try if you get really, really stuck and want to talk to somebody. We have a yearly developers conference called ROSCon. It's going to be in the US this year, so if this is something you're really, really interested in, perhaps you should look into going to ROSCon. It's going to be in New Orleans, so that should be fun. We're not huge social media people, but we do have a couple of Twitter accounts. I'm secretly behind those, so if you have questions or problems, I'll probably be answering them, or you've just taken all these lessons to heart and built something super cool and like to show us, just let me know. And then you can also just check out the Open Robotics website. It's basically some of the events that happen, some of the news that comes up. We post stuff there on it periodically. Before we begin, I just wanted to cover a little bit of history of ROS, because sometimes people see these things and they see them in the context of modern development, and they don't understand that the reason sometimes the way things are structured is because ROS is developed over time, right? And it's developed over quite literally decades at this point, and where it all came from. And I think giving a sense of that history would sort of help you understand why things are a certain way, and I think that's helpful. So if you go back to the early 2000s, open source is not in the sort of primacy role that it is today. And so it's growing, but sort of Windows dominates. And robotics is still stuck in this before the turn of the millennium phase. And the robots are big, expensive capital equipment that are mainly used for manufacturing and R&D. and they're mostly running sort of real-time control systems, and they're moving arms to do manufacturing, and there's not a lot of open source. So about 2006, some former Google VPs decide that they want to go work on robots. Why don't we take all this Google knowledge and we try to apply it to robots? And they sort of created a company called Willow Garage in the spirit of something like Bell Labs or Xerox PARC, and let's just get a bunch of smart people in a room and let them go build stuff. And from this org, we got things like OpenCV, PCL, ROS, the PR2 robot, and a bunch of spin-out startups. So Willow was around for a long time. There's actually been some documentaries on what happened there, and then approximately 2012, Willow folded, and then sort of out of the group of people that were working there, Open Robotics emerged. And so Open Robotics worked on ROS2 for quite a while, or ROS for quite a while. And then about 2017, we decided to sort of take all the feedback that we had gotten in prior years, and all of these things that made people say things like, well, ROS is a great utility, but it's really only helpful for academics or research applications. Well, let's go and fix all those things. Let's understand what the problems are and address them so we can really build a system for these next generation robotic applications. And, we started looking at things like addressing security concerns and robustness concerns and quality of service needs. And let's put those all into a new version of ROS that gets things ready to really go out in their field and to build these autonomous vehicles, to build these sort of next generation manufacturing applications, drones, all of these things. Let's actually build them for the long term. So before we begin actually talking about software, and there's a lot on this slide, and if I had all the time in the world, I'd say this slide really should be a whole hour or two of discussions. Because to understand what ROS is, you have to sort of understand where it came from and all of this sort of software design patterns that motivated how ROS is built. So I wanted to touch on them briefly. This is all sort of cross-referenced with appropriate Wikipedia articles and everything else. And I think it's really, really helpful that before you begin, or after this lesson is done, it might be helpful to go and look at these things, because I think if you understand the fundamental design pattern of why we built something some way or what has been used from the past, you'll have a much better understanding of what ROS is. So let's take a look at a couple of design patterns. The other thing is that I've structured this a little bit as an analogy. So if you're coming from, say, a web dev world, I tried to point to the things that I think are fairly analogous. So let's start with ROS nodes. If you're familiar with, say, creating a new process or a new thread, a ROS node is basically a process that's running inside of ROS. And it's just a self-contained execution thread, just like a program. And so whenever I say node, you should just think, oh, a ROS node is basically a program. Another thing that comes up fairly often are ROS topics. A ROS topic is basically just a structured message on a pub/sub bus. So pub/sub basically means publish subscribe. If you've ever used something like ZeroMQ or RabbitMQ, or even in the hardware world, something like Modbus, they're all very analogous to what's going on in ROS, in the sense that you have a bunch of different devices and different threads of execution, and what they do is they just publish repeated messages over and over and over again, or they update them with new data, and then you can listen to those and make choices based on what you've heard. So if you've used RabbitMQ or ZeroMQ or something like that, just whenever I say a ROS topic, just think, it's a ZeroMQ queue. Another big thing that you should be familiar with or try to understand is serialization. So in ROS, our serialization format is effectively something called a ROS message. And these ROS messages can be used and sort of stored in something we call a ROS bag. What ROS does underneath the hood is you define basically a YAML file with what your message is, and then the whole system can basically serialize and deserialize those messages between different nodes. If you've ever worked with Google protocol buffers, it's fairly analogous. Another way to think about at least ROS bags is if you've ever made a Python pickle file, it's kind of like that, where it's like, let's take a bunch of data and serialize it out and give you a way to replay it and get in there. Another high-level concept that I think is useful for understanding is ROS params. So ROS params sort of come from what's called a blackboard pattern. A blackboard is like if you go back to say the 1940s or something, right? There'd be like, if you wanted to communicate a bunch of information to a room full of people, you'd have a blackboard and you'd say like, what is the value of this? And you'd write in a number, and then somebody else could read that number, and then if it changed, you just erase it, put in a new number. Well, that's the blackboard pattern. It's just a way of keeping an ordered set of parameters. If you can kind of think of it like Redis in a certain sense, like it's just basically key value pairs. So you can go and find one and get its value or change its value. Another core concept that we'll cover today are ROS services. A ROS service is just basically a synchronous remote procedure call. So if you've ever sort of read about remote procedure calls, this notion of, hey, I have my computer, I have that computer over there, I want to execute some code on that computer over there via remote procedure call, that's essentially what a ROS service is. Similarly, we have ROS actions, which are the sort of asynchronous remote procedure call. They're a little bit more complex. So generally, the canonical example that you would use with a ROS action is I'd want to create an action where I can tell my robot, hey, go to that point over there and let me know once you get there. So an action is this asynchronous remote procedure call where you say, hey robot, go do this thing and then send me periodic updates as you get there or don't get there. So those are all the sort of core topics. I know that's a lot to cover and to digest, but I wanted to make these analogies up front, so hopefully you can kind of swap them out in your head while we're going through stuff, and it'll help you understand. All right, so let's jump right into the deep end. Let's start ADE and basically install and update our dependencies. So basically at this point you should at least have ADE installed. It's probably a time to pause the video and run the commands underneath. I've already done this, so we're not going to have to wait. But what we're going to do is install ADE per the Autoware instructions, and then we're going to add, we're basically going to install ROS dashing and a couple of tools. So here in my terminal, actually I'm going to turn this up just a little bit. ADE start, get into our VM, and it's already running, so we'll do ADE enter, and let this queue up. There it goes. Okay, so now what we're going to do is, first thing on all ROS systems that you always want to do is we're going to source our setup.bash file. And what this is going to do is basically in this terminal tell the terminal, hey, we're running with this version of ROS. So what we'll do is source this file, and on this machine it is, on most machines, it's in opt ROS dashing setup.bash. And if you're not familiar with Linux systems, you can use tab right there to sort of help you autocomplete all of those things. You don't have to type that whole thing out and try to remember it. So on the left, what I suggest you do is do a sudo apt update. And if you're not familiar with Linux, apt is basically a program that's it's an installation program. It'll basically install a program for you. So apt update, so we update our list of programs. We're going to install ROS dashing turtlesim, ROS dashing rqt star, which is just all of the Qt related GUI apps. And then I personally, as a terminal manager, like to use Biobu. If you use tmux or something else, feel free to use whatever is comfortable for you. If you have a sort of IDE or perhaps a text editor of choice, you might want to install it now too. Okay. So we've got everything ready. So let's talk about a little bit of nomenclature before we even begin. So basically ROS is built upon packages. And a package is just a collection of code. It can be C++, it can be Python, sometimes people do Java or Go. Those are less common, but it's just a collection of ROS code that is particularly published and perhaps somebody has released on the web and that you can also pull down and use. Along those lines, there's also this notion of a workspace. And so a workspace is just a collection of source code and ROS packages that we want to deploy on our robot. So generally what's going to happen is you're going to build a robot, you're going to build an autonomous vehicle, and it's going to have a workspace that defines all the packages that are on there, all of your sort of client code that you want to run. Again, by analogy, a good example of this would be a Python virtual environment. A couple other bits of nomenclature that might be helpful is an overlay. An overlay is basically a second workspace with more different new related packages. If there are multiple versions of a package code, then the one at the bottom is used. So in a sense, like if you create a user space, that's going to be the overlay. If over and above your system installation of ROS. There's also this notion of underlay, which is the workspace underneath the overlay. I'm aware this is confusing. It's not the best nomenclature, but essentially the way to think about it, if you're familiar with Python, is I kind of like to think about it as like layering virtual environments on top of each other. And yes, that's really complex and problematic sometimes, but the reason we do it that way is sort of to allow people to have multiple systems to do what they need to do and build up capabilities. And the other thing I think I need to mention at this place is people often get stuck on this. The stuff is hard, it's confusing, it's sort of complex, and the short of it is that you need to realize that ROS is this ecosystem of tens of thousands of developers working on thousands of packages across like a handful of platforms on multiple languages, and all of our build system and all of these sort of complex things are there to allow us to make that happen. Okay, so let's get started. So as we're diving headfirst into ROS, our first job is to check out a repository of examples and basically build it. The steps to do this are really simple. You fire up your terminal manager, and enter ADE. So I'm already in ADE, so I'm going to go terminal manager. Cool. And just for safety's sake, I'm going to source our opt ROS dashing bash just to be 100% confident that I've sourced it. And what we're going to do really quickly is we're going to make a workspace called ROS2 example workspace. So you just, if you want to follow those examples below, so you do make dir, and I've already done all of this, but essentially you make dir, and we're going to call it ROS2 example workspace. Or ROS2 example WS, where WS means workspace. And we're going to create the source file. We're going to cd over to that directory. We're going to clone this GitHub repo, which is full of ROS2 examples. And we're going to go over there into that directory, check out the dashing examples. Now we're going to go to the root of the workspace, and we're going to run this command. So let me get over there real quick. And we're going to run the command. So ROS uses a build tool, or a build system, I should say, called Colcon. And Colcon it's not a build tool. Underneath, it's basically taking a bunch of different build tools and allowing them to work together. And that's the way you should think about it. So, you know, if you're using Python, right, your build tool is going to be something like setup.py versus like C++, your build tool is going to be CMake. And so Colcon is sort of this layer that sits above all of that to help organize everything and allow you to build these very complex ROS projects where you might have Python interspersed with C++. And that's what's really cool about it. So let's go run this real quick. And I've already built it, so it shouldn't take too long. And we're going to do a symlink install. Cool. And so what Colcon just did is it actually built 15 different packages, right? So it built all of the example packages that are in this repository, and it did it all fairly quickly. And we can see here it basically started this minimal action client, it started this minimal action server, etc., 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 and it built all of these. And these are all sort of separate packages. So let's go to the next one. All right, nodes and publishers. Okay, let's talk about nodes and publishers. So the core of ROS is the sort of ROS pub sub bus. And in ROS parlance, we like to call a publisher um, is a topic, right? So a topic has a message type that is published on a particular has a message type that's published on a particular topic on this sort of pub sub bus. These messages are defined in a YAML file that defines the serialization and deserialized format for ROS messages. ROS has a lot of built-in message type, and there are a lot of really good predefined messages for controlling a robot, or distributing sensor data, or understanding the geometry of a robot. If you find the case that you need to make your own custom message type, you're probably doing something wrong because there's so many of them at this point. And you're probably better off extending something that already exists because there's already tooling that exists for a lot of common message types. A ROS publisher can produce messages as slowly as quickly as it needs to, and once it's published, you can have a ROS subscriber that subscribes to that particular topic and then gets those messages and does something with them. The ROS topics themselves have a lot of tools for management. So you can list them, you can echo or watch a topic, you can rename or remap a topic, and you can store all the data coming across on a particular topic in a serialization format called a bag. ROS nodes are basically programs that or processes that run concurrently on ROS. A ROS node can have one or more publishers, a ROS node can have one or more subscribers, and many nodes can subscribe or publish to topics that are already out there. And ROS also has a lot of tooling to start and stop these nodes and bring them all up at the same time. So let's go to the next slide. So preparing to run a ROS node. So why don't I suggest you open up a new terminal. You can do this by pressing F2 and Biobo. First, what we need to do is to source the setup.bash file for our ROS2 workspace. So to do this, we just do source / setup.bash, and what this is going to do is it's basically going to tell the terminal, hey, this is where I'm going to put all your programs, this is where I'm going to put all of your stuff that we build, and you know, it kind of acts as a namespace or a workspace for whatever you're building on. It's generally recommended in ROS that you build in one terminal and execute in another terminal, and this sort of helps. So in one terminal where you're building, you're going to be sourcing just the setup.bash file for the version of ROS you're running, and then the next one you're going to be sourcing the bash file inside of the workspace. So you're saying, in the first one here I'm just using dashing, and then inside of the workspace that you're actually running your code in, you're going to say, I'm using ROS dashing inside of this workspace. And that's generally how you work. And if you encounter problems, this is just the #1 beginner problem that happens. Make sure you've sourced the correct setup.bash file. So we've built, or we've sourced the correct file. Let's go and run a node. So what we're going to do first is we're just going to simply run a simple C++ publisher node. And all this publisher node does is it's got a topic, a single topic called message, called topic, and it's just going to take a simple string message type and push out a string every at a certain frequency. The way we're going to run this is we're going to use the ROS CLI. We'll cover this in depth next time. And we're going to run an executable called publisher lambda in the package called examples rcl cpp minimal publisher. The general syntax for this command is basically ROS2. So we'll do ROS2 run, and then the package type. So the package type here is examples, and you can tab complete this, so it should really help. So we're running RCL, so ROS Common Library CPP minimal publisher, and then we're going to run publisher lambda is the executable. And we'll hit enter here. Oops, must have misspelled something. When in doubt, we'll copy and paste. So boom, copy, paste, enter. And if we did everything okay, we should be seeing this. And so we're publishing on a topic, and it's just saying hello world, hello world, hello world, and then giving a number. So it's kind of a sequence number. Every time it sends a new message, it updates the number. So what just happened? We just executed a ROS node that publishes a simple string message to a topic called topic, and it's publishing at 2 Hertz, so twice a second. And we can actually, if we open up a new terminal here, I'm going to press F3. We can actually inspect this topic. So I'm going to show you a little bit of this command line magic. We're covering it in depth next time, but we can go topic list. We can see all the topics, and we can see that we have a topic called /topic, and topics are kind of names in the same way that you would name, say, something in a file system. So you can have like my node / topic A, topic B, topic C, and that's how you sort of segment the different kinds of data that you're spitting out or digesting. We can run a command line tool to actually see what's inside of this topic. So we can do echo topic. It should output a message. Yeah, I see 156, 157, so it's still going up. Control C will exit out of these programs if you get stuck. And we can also see what rate it's running at. So we can go ROS2 topic and then Hertz. And we want to look at /topic. And we do this, it'll actually tell us how fast this topic is running and give us a general idea of its performance. And we can say it's just running right now at approximately 2 Hertz. So kill this. So why don't we dig into the code? If you, since this is ADE, you can either use your favorite IDE on your sort of host system if you want. I'm just going to use less and like Emacs inside of ADE right now for simplicity, but you can kind of pick how you want to do this. And if we want to go look, this file is located in /source, and then our example repositories. And we're looking at the C++ examples, so it's in RCL, ROS Common Library, CPP, and it is in the minimal publisher, and it's in this directory. Let's just make sure. And the function we're going to want to look at is member function CPP. And when it says member function, we're going to look at a publisher that is a publisher as a member function in a big class. So let's open this up, and it's also on the left too with syntax highlighting, so we can take a look at both. So what's going on in here? I kind of abbreviated it here on the left, but we can see if we look at our includes, the first include here is this RCL CPP /RCL CPP.hpp. So this is just a header file that's saying, hey, we're using ROS, we're using CPP library for ROS2. The next include is standard messages string HTTP. And what this is a basically an automatically generated header file that gives the serialization format for your message. And this is all auto-generated by ROS, so you don't even have to think about anything. You just need to include it in your source code. And if we look through here, we also have namespace. And then we define really quickly a class called minimal publisher, and this class inherits the public interface to RCL CPP node. So basically what we're saying is, hey, we're creating this minimal publisher class that is a ROS C++ node. Cool. So close this real quick. Let's go to the next step. So let's take a look at the node's constructor. So if we scroll down here just a little bit. Alright, so we have this minimal publisher, and what it's going to do is it's going to inherit from the base class, and we're going to give it a name and a counter. right? So there's just a member variable called counter. That's the 1, 2, 3, 4, 5, whatever number that gets published. And we're going to give it a name, which is minimal publisher, and this is the same name that we're going to call. Let's see, and we're going to create a publisher that pushes standard messages dot message to the topic. So we create this publisher, or we take this variable that's publisher, and we say create publisher, where the type is standard message, messages, string, and we're going to call it topic. Then we're going to create a little timer that calls back every 500 milliseconds, and we're going to bind that to the function called minimal publisher timer callback. So if you're not familiar with bind, all this is saying is that it's a callback. So it's a function that's going to get called at some regular frequency. Let's go to the next slide here. So let's go take a look at how this callback, which is the thing that's going to get called twice a second, that is going to publish a message, what does it look like? So it's a private member function, and it's got a type, and new C++ auto here, so auto message, and we create this standard messages string type, or string message type, and it's got sort of a member variable called data, and we just say, hey, it's going to say hello world, plus a standard string of the number, which is the member variable of our class, count, and every time we call this, we're going to increment it. And then we're going to call our logging function here, and we're just going to say, here's an info message, send it to the logger, we're publishing blah. And then, if we look over here, we're going to call our publisher member, and we're going to say, hey, call publish on this message. Pretty simple. And then below this, we just have our private member variables. And that's all there is to this. And then if you look down at the bottom, there is, let me scroll over here too, there's just a main function. And the main function is just calling the ROS C++ interface, and it's passing through the argc and argv to our program. And we're saying, hey, spin this process, spin this node on this thing called this class that we've created called minimal publisher, and just keep calling it with the callbacks that are in there all the time until we say shut down ROS. And then ROS shuts down and we return 0. And basically when you call this shutdown, it'll help clean up everything, and that's it. So let's go. Alright, so why don't we do a little quick exercise here. And we're not gonna write a ton of code, but I think it's good just really quickly to do it once. So the lesson, so I'm actually gonna open this real quick. Function. I'm gonna use Emacs. You can use whatever you want. Okay, so why don't we try to do a few things here. We're gonna make this run a lot faster. So we're gonna make it run 10 times a second. And we're gonna change the topic name from topic to greetings, because that's really, topic's a bad topic name. You should give it something a little bit more clear. So we'll call it greetings. And we'll change the message too. And we'll also change its name from minimal publisher to revenge of minimal publisher. So why don't we go through and do all of these things. So the first thing we want to do is change the rate. So instead of running every 500 milliseconds, we're going to make it run every 100 milliseconds. And we're going to change the topic name. We see here it's called topic. So we don't want it to be named topic. We want it to be named greetings. And what else did we want to do? Oh, we don't want our node named minimal publisher anymore. We want it to be named revenge of minimal publisher. So we'll change its name to revenge of minimal publisher. And oh, we want to say one more thing. So since we're doing a self-driving car course, we're going to say, instead of hello world, hello open road. And we're going to save all of this. And we're going to go back back up a couple directories. 1, 2, 3, 4. Went too high. And generally, like I said before, we don't want to build over here, so we're going to go back to our building. And we're going to say :build. So we're going to use our build system to say build all this stuff and reinstall it. And it's building. No errors. Cool. Go back over. Kill this, which was still running. And what we can do is, I'm just going to copy this. Paste. Did we do everything? Yes! And we can see this is publishing a lot faster. It's changed from Hello World to Hello Open Road. And that's about the sum of it. And the node's changed, right? Because we can see the command has changed. So instead of running the packet or the node name has changed here. So it's now Revenge of Minimal Publisher. Cool. I'm going to kill this. Okay, so the next thing we're going to try is we've created a publisher. Now why don't we go look at building a subscriber. So we want something that is taking this message that we're publishing and basically absorbing it, looking at what's in there, and then doing something with it. So the sort of example to think about this is a lot of times when you're doing data processing, right? There's a stream of data coming from, say, a sensor, and you want to go and process that sensor data and clean it up or make a decision based on it and publish a new message. So I don't know, say you had a wheel encoder and the wheel's going, you know, the encoder just gives you clicks and you want to go from clicks to velocity. So you'd make a node that basically there's a node publishing the encoder clicks. You create a new node that takes on that click topic and takes and then processes it and publishes, you know, RPMs or something like that, right? So we're going to create something, subscribe to our topic and do something with it. So why don't we take a look at this? And this is basically in the minimal subscriber example. So in your favorite editor or using less or whatever you want, we can go grab this, grab it right here. So I can open the file. And I also have it on the left, but I feel like it's good just to have it in both places. So let's take a look at this file. And what is it made out of? What is the subscriber doing? Well, we can see here that it's still including the same header file, just like before. Hey, we're using the ROS header files. We're going to be using the standard message screen. We're going to have a placeholder, and then we're going to create this class. And we're going to create a class called Minimal Subscriber that's also inheriting from the ROS Common Library node interface. And it's going to be named Minimal Subscriber. And in the constructor, we're going to create a subscription, and this is sort of coming from the ROS node API. And we're going to subscribe to a message of type standard messages string. And we're going to say off the bat that we're subscribing to something called topic, and we're going to bind to that topic. And whenever we get, and then here's the last little bit that's actually really useful, and that is that whenever that topic that we've subscribed to, or that message that we've subscribed to, gets published, we want this function, minimal subscriber topic callback, to get called. That's all that's going on. So let's go back, and I'm going to scroll over here a little bit. So let's take a look at the topic callback. So this is going to get called every time that we, the topic that we subscribe to, that a new message is published on that. And this call basically gets a standard message string, and it's just a shared pointer to that message. And inside of here, all we're doing is we are writing to ROS logger, and we say, I heard this message, and we go in the message and we get its actual data as a C string, and we publish that. And if we scroll down here just a little bit, we can see that we're basically using the same pattern all over again in our main entry point. That is to say, we initialize ROS, we say, hey, we're making a shared memory pointer to this thing called minimal subscriber, or this class that we created called minimal subscriber, and we're calling the spin function, which is just going to keep calling it basically whenever something happens. And we're going to do this until ROS gets told to shut down, and we'll return 0. So let's do this. Go over here. So in the publisher, we changed the name. Why don't we go in and start looking at how we can modify this publisher? So let's edit it. And I'll change this over to my editor. Why don't we do this in the window? Okay, so why don't we change, as just sort of a learning what's going on here, why don't we change what it's subscribed to? So we changed the last thing from publishing to topic to greetings. So why don't we subscribe to greetings instead? And we can see that it's here. It's where it says topic. We can just say, no, you're not subscribing to topic anymore. You're subscribing to greetings. And I think the thing that's worth noting here is that you can change this in code, but there's once we get into some more advanced topics in ROS, you can actually change this program, or you don't have to change the compiled code for this. You can actually remap it. So remapping is this concept where instead of manually changing this, we just rename it at runtime, which makes things a lot easier. So once we have this all built and saved, we can go back over here and we can rebuild. And let's see, let's fire up our guy here that was publishing on greetings, and we'll open up a new terminal, press F3, and what we can do is we can now run our subscriber that's going to listen to this, and every time it hears a message from the other node, it's going to basically spit out a response. Now we can see here, you see how it started really quick up there, like at 195? So our subscriber now is saying, hey, I heard this other message. I'm a completely separate node. I've heard this other message, and I'm just basically spitting it out. So this is pretty cool. It's this is a very primitive example, but basically we've now connected these two nodes that are running concurrently. One of them spitting out messages, another one's basically digesting those messages and doing something with it. It's not that complex, right, because it's just string parsing right now, but we can see how we can build much more complex systems with this as we go along. Right, and so we can see all this one side the other. And let's go ahead and kill all of these, and I'll kill this one. And so I think the thing that's interesting here and that we have to remember is that, you know, we've just built a very primitive ROS system, right? We have two nodes, one's publishing, one's subscribing, they're spitting out data and taking in data and doing something with it. And while this is really simple, it's the basis of basically how most ROS robots work. All right. So we've covered the basics of ROS, right? We've talked about nodes, we've talked about publishers, we've talked about topics, we've talked about subscribers, we've talked about all of these pieces that are sort of the building blocks of ROS. But we're still missing a bit. And the bit we're missing is that right now we know how to process data, right? We know how to get data in, how to do something to it, to spit it out. And that's good. We can understand the world around us, but now we need to make things happen based on that data. And in ROS, there's basically two ways that you do that. There are these things called services that I'm going to talk about right now, and then I'll talk a little bit about actions, which are the second bit. So a service is, the simplest way to think about it is it's like a fancy function call in ROS. And services are for anything where you think a robot can perform a task synchronously. A good example of a service, a toy example of a service call in ROS would be, let's say we take our autonomous vehicle use case, it'd be something like, turn on the lights. Check the sensor really quick and just give me a value. unlock the doors, beep the horn. These things that happen, you know, real time or fast or synchronous, all of them are hard to define, but things that happen like while you wait. So you're just like, go do this thing, I'll wait for you to do it, and it comes back. And all of these things can be done in a ROS node. So a node is basically the container, is the executable container, and a service is something that the node does, or that it offers to the other nodes to be done. So let's take a look. So as a toy example of a ROS service, we're going to make a node that offers an add to int services. It's the stupidest possible service that's out there. It basically is a very, very complex way of saying, here's A, here's B, please add A and B together for me and return the results. There is a full tutorial on how all of this is done. I'm not going to cover it in super duper depth because there's some steps I'm going to kind of gloss over. There's a link in there. You should go take a look at the full tutorial and it'll lay things out for you. So before we talk about how the service is constructed out of code, the first thing we should do is talk about sort of how we define a service. So in ROS, there are these things called serv files, SRV files, and what they do is they basically define the inputs, define the outputs of a service as a YAML file, and from that YAML file, we generate a bunch of message types and headers that can then be used in the executable code for your node. And what's actually secretly, don't tell anyone, is going under the hood is that it's kind of, I believe, built on top of some of these topics. So why don't we take a look at a predefined service file. It's in kind of a funky location because it kind of comes shipped with the desktop examples, but what we'll do here is I'll open up this file called add2ents.serve right here, and what we'll see is that there's basically int64, which is type, right, A, int64 type B, and then 3 dashes, and then int64, which is a type, and sum. And this is defining the service. The things at the tops are the inputs, the things on the bottoms are the results. And you start your service by like just defining this file. All right, so I'll close this file and go over here. All right, so in ROS, once you've created that service file, what Colcon will do is it'll take it and it'll auto-generate all of these things that you'll need, all the header files for all the different sort of languages that are supported. And it'll make them for you and make all the sort of types that are associated with it, and then you can just use them in your code. So you don't have to think about it, it's just sort of magic. So why don't we open up our favorite editor to, let's do right here. So I'm going to open this file called, it's in our workspace, source, examples, RCL, CPP, minimal service, main.cpp, and open the window. Ta-da! Cool, that works. Check that. Okay, so let's take a look at this, and we'll gloss over it. It'll be pretty interesting. So we look at right at the top, like I was saying, hey, here's this, here's path to an included header file that basically defines the add2int services, include file for ROS Common Library. And then what we do, first thing here is we use this using directive to basically say, hey, this thing called add2ints, well, it's actually example interfaces, scope resolution serve, scope resolution add2ints, but you can just call it add2ints. And then we also create a shared pointer to basically ROS, or ROS node. And we'll see right here at the top in this service main, handle service, which is just a function call. Right, so what do we have in this function call? Oops. Do this. So in this function call, it's called handle service. And it has a shared pointering to a request header. Request header is just basically a baked-in, predefined thing that you can look at to say when was something sent, who sent it, why they sent it. Think of it as like the address on a piece of mail or something like that. Then we have a shared pointer to an add2ints type request. So that's going to be our A and B. and then we have a shared pointer to an add2int response, which is just our sum. And then if you look in here, basically all we do is we say we got these things, we add them together, and down here we say response. There's this thing called sum. Take the input A, take the input B, shove it into sum. Cool. And that's it. That's the all of it. And then all we have to do to make this work is we create a main right here. We initialize ROS. We create a node called minimal services, and we create the service called add2ints, and we bind it to basically this function call called handle service. And then we tell ROS, hey, just keep this thing running until we shut down. And that's it. That's all there is to it. Yep, I already went over all that. Cool. All right, so now let's build and run the service. So this should already be built. The syntax for running a service is pretty simple. You should kind of be getting the pattern here. It's ROS2 run, and we're going to run examples. ROS common library, CPP, minimal service, and this thing is called service. Main is the executable. We hit enter, and nothing happens. Why is nothing happening? Because we haven't sent a request. So what we need to do is send it a request where we have an A and a B so it can send us back a sum. So we'll do this just in the sake of example. We'll do this via the command line, and then we'll do a client bit of code that'll show you how to do it in software. The way you make a service call is, well, actually, let me show you this too. So what we can do is ROS2 service list. You can see what services are running. And we can see that our add2ints service is already running. And so what we can do is so the only difficult part about this before I do it is that we're going to send the service request and we have to define the message correctly in the command line, which is kind of ham-fisted. You have to basically say the path to the type, and then you have to kind of write the type. So it ends up looking a little bit weird. But what you end up doing is you end up saying ROS2 service call add, yep, and it tab completes, add2ints. And then I gotta grab this bit right here, example interfaces. So we're giving it kind of the path to the type, and then we're giving it the type, and we're just gonna add 1 to 1 here. And I hit enter, and we can see waiting for service to become available. So what it does is it checks that the service is there, makes the request, and then gets the response, which is 2. We can just approve that there's nothing up my sleeve. We can make this like da-da-da-da, and these are 64-bit ints, so I think we should be okay. Yeah, I'm gonna assume that's correct. And we can go back over here and we can see that the service itself has said, yeah, somebody requested this, some weirdo requested this. This all works. Sweet. All right, so why don't we figure out how we can use this service in another code. So we're gonna make one node that has a service running, we're gonna make another node that calls a service, and we can kind of get the feeling of this pattern. So I'm gonna go back over here, leave that guy running. And why don't we open up this minimal service client right here and take a look at the code, and then we'll run it. Paste. And I'll keep this in here. All right, so let's see what's in here. Well, we see our familiar pattern already. Include the service header, add2ints.hpp, include the ROS headers, and then also this add2ints scope resolution. Totally cool. And then all this is, it's a main. We init ROS. Basically, we make a node called minimal client, right? So we've created a node right here. And then we say create a client to this, and this is a little bit tricky, but create a client, and this is the type here, right? The template type is add2ints, and it's named add2ints. This will get you every time. You just have to be very, very clear. You can see how we sort of set a pattern here where the type is add2ints, and then the name in camel case, and then the runtime name is underscored, right? So there's two different kinds. So we're trying to show you a good pattern here for keeping these things straight. Otherwise, it'll bite you in the butt every time. All right. So then what do? Well, we tell the client to wait for the service. So wait a second and check that the service is there. So it could be the case you could start this node and there's no client. So it wouldn't do anything. It couldn't call anything. So you need to check that it's there. If it's not there, throw an error. And then let's go down and go forward here, and let's see what we do. So we make our request. Auto types are great, right? So you say standard make shared add2int request type. I know it's kind of convoluted, but now we request, and we know that it has an A and it has a B. So we set their values. We're going to add 41 to 1. And then we create this asynchronous request. So we say, okay, our client, asynchronously send this request and call us back in the future whenever this thing gets done, right? So basically we just kind of wait, we check its sort of return value, right? So this result futures thing, you can basically spin it and it'll return some value, and we're hoping it's success, but if it's not success, we'll spit out a bunch of garbage and say, oh, it failed for some reason that we don't know. If it completed successfully, we'll just get the result and we'll log it and we'll shut down. Cool, right? So let's close that. And now let's go run this client. So I'm already in a new window, so I don't need to open it up. So all we have to do, and let's double check here. Service is still running, cool. So all we need to do is call this thing, which should be ROS2 run examples. Oh, we want the client. Minimal client, and then it's client main. Boom. You see, so you see it's sent right there, and then it got the result. If we toggle over to their other terminal, you can see it came in. Cool. So that's fairly straightforward. Close this. So that's fairly simple. So now let's talk about action. So we talked about the simple case where it's like, hey, I want to send you this thing, just do it, send it back real quick. Not a big deal. But some things that a robot might do aren't that simple. And so the kind of canonical use case that you'd use is like a navigation use case. So you have this robot like a turtle bot. I got one right here. Kind of. It's not exactly running. Right, so it's right here. This little guy, hang out, you say, like, okay, Turtlebot, you're on the floor, I want you to go over there and, like, do something cool. So the robot doesn't instantaneously teleport from over here to over there. It takes time, and things happen. It's like life things happen. So, like, the Turtlebot, like, there could be something on the floor it runs into, batteries could fail, I could go over there and kick it. So there's, I want to request this thing, but it's unsure if it'll happen. And so we have these things in ROS called actions. And actions are there for these sort of asynchronous, will take a while request things. And they're basically the preferred approach for doing things that may not happen instantaneously. And so there are basically multiple parts to an action. And you're also going to have both an action server, where it's the thing that does the thing, and the thing that asks for the thing to be done. So there's a client. And actions can also, the thing about how they're structured is that you can have an action server that does the thing, and it can have multiple clients. So like if you imagine in an autonomous vehicle, something that may not happen instantaneously, even though we'd like it to, is like, stop the vehicle. Especially if you're on the highway, right? So it's got to go through lanes, you got to like signal through traffic maybe, but you really want to request that the vehicle stop. So you might, in a running ROS system, right? Let's say there's a node that's like one node that's doing radar or something. It says stop, and there's another perception node that also like sees something in front of the vehicle and wants to say stop, and they might say stop simultaneously. And so the action server has to be able to say, oh, I got too many people, somebody else already asked me to stop, this guy asked me to stop first versus this other person or other node. Another thing that might happen, other than this multiple clients coming at the action server at once, is this notion that the client may ask you to cancel. So an example of how that might happen is you're driving along, the car's running, and the perception system, I think I've heard of this actually happen. So there's like a plastic bag. We've gotten rid of those in California, thankfully, but plastic bag is getting blown across the road, and the perception system freaks out and doesn't know what to do with it. It's like, I don't know what that bag is. I'm going to assume it's a person. We should stop. And it will issue it'll ask an action, the stop action, to stop, and it'll start, the action will do, okay, cool, I'm going to do that, and it'll just start slowing down the vehicle. And meanwhile, the perception system says, oh, that wasn't a person, it was a bag. Cancel that stop, we can keep driving. So you need to be able to cancel these actions in the middle of things too. So it's a bunch of different stuff you're going to have to handle. It's a little bit more complex, but it's also a little bit more robust and handles all of these sort of real world use cases. And so, a lot of magic can kind of live in there. Oh, I screwed up my slides. So, parts of an action. Basically, when an action starts up, you need to find the action. The action server may be down, so when your action starts, if you're a client, you need to say, like, is the action server up? You need to make the request, and often as a server, you can say, no, I don't want to do that. Yes, I can do that. So there's a sort of, back and forth on the initial request. And then the action is accepted. The action, can then go along and it'll give updates, saying, like, in that sort of stopping example, the action might say, okay, I'm changing lanes, then I'm slowing down, now I'm coming to a complete stop. That feedback needs to be sort of given to the client and maybe to other people or other nodes as well. All along that time frame, somebody might come in and say, cancel, and you have to handle that. And then there's the final, like, everything's done, I'm just going to send it back to you. Like, the action has been completed, we're all done, here's the result, cool, everything's over, the transaction's complete. So as sort of our toy example here, what we're going to do is we're going to create a Fibonacci action. So if you know the Fibonacci sequence, basically, 0, 1, 1, 2, 3, 5, 8, so on and so forth. So we're going to create an action that you request the nth order number in the Fibonacci sequence, and the action will spit out each successive number until it calculates the one you want, and then it'll return the whole thing. And you should be able to cancel and do all these other things. I'm not going to do all of that in the sake of time. I'm not going to do all of those different steps and show you how they're all handled, but they're all in the code base, in this example code base, so you can go there and kind of get a sense of how they're structured. So let's start taking a look here. So just like before, just like services, actions, use an action file, just like a service file, to define the parts of the action. They don't define all the parts because they don't define like cancel, but all of the like request, the final result, and then the feedback steps in between, those are all defined in the action definition files. So why don't we take a look at one really quick. And these are all written in YAML, I believe. So if we do all right, so here I have one. It's pretty straightforward. So the goal, it starts out, it's always first the goal. So the goal here is just going to be an integer, which is the order or the sequence number in the Fibonacci sequence. So in that, like, each number is 1, 2, 3, 4, 5, 6, 7, 8, 9. So whichever one you want up to a certain number. There's the result, which is the sequences of actually calculated numbers all the way to the nth order one. And then finally, there's the feedback, which is sort of the intermittent growing list of numbers that we're going to send all the time. Okay, so let's exit this. And just real quick, just to show you kind of what's going on underneath the hood here. Let's go here. The action is used by ROS, is used by Qualcomm to build messages, like ROS messages, that define all the different sort of bits and pieces of this action, and they're all sort of strung along as sort of internal topics on a node. And let's take a look at this. So I've moved over to this directory here, and what I can do is ls, and this is from the Fibonacci action that I just showed you. And what you can see here is that there's the action feedback message, there's the action result message, there's all these different messages, right? And they're all auto-generated from that initial action message, which is kind of cool, right? It just saved you a bunch of work. It defined all these things automatically so they're correct. It's quite handy. All right, so why don't we take a look first at our action server. I'm going to go back home and go ROS2 example workspace, source, examples, RCL, CPP, minimal action server, and then we're going to look at, let's see over here, and we're going to just open up member functions. So a couple different ways to do this. I'm going to show you how to do it as member functions inside of class, because I think that's sort of the most intuitive way. So let's take a look. So standard headers, include directives. At this point, this here should be no surprise, right? There's an automatically generated header file for all these message types, and you need to include it along with the ROS headers, which is cool. And then what do? It turns out our action server is just a node, just like before. And then we have a public interface. So, and we use a couple using directives so we don't type too much. So we basically say, hey, a Fibonacci is actually the interface, example interfaces, actions, Fibonacci thing. And then the goal handle is actually the goal thing of this type, template type. Cool. All right, so then let's actually instantiate this guy, or not instantiate. Why don't we take a look at this action server and its constructor, and it basically takes in a couple options and is given a name, minimal action server, and uses those options to the base class. And then we say, hey, we're using this namespace. And we say, internally, it's got a pointer, or this action server is going to equal create a server of type Fibonacci. and we're going to basically pass it some information about the calling node's sort of interfaces. So all this is doing is saying like, hey, this action server lives inside this node. This is where this node is logger is. Its waitable interfaces. This is where its clock is. So you're just saying that. You're giving it a name. And then this is where things kind of get interesting. Because what you're doing is you're saying, here's my thing. And it's a little hard to read without the definition right in front of you. But basically saying, hey, when you need somebody to handle your goal, bind it to this function called handle goal. When you need somebody to handle cancel, call this function handle cancel. And when you need a function to handle it being accepted, call this. And that's it. So let's go look at here. Let's scroll. Oops. Let's scroll down here into the private member functions and see what's going on. And what's this? This is just a shared pointer to the action server itself, or the sort of base class. All right, and so when we handle a goal, we're going to take in a UUID, and so this is a goal request, right? So like I said before, you might have multiple people asking, so they need like a unique identifier. So that's what that is. And then shared pointer to a goal, that's just the input. And what do? We say, here's our goal. We check to make sure that our goal is less than a certain number, so we're not here all day. The thing you need to note here is just how you return the type, right? You can basically say, screw you, I don't want to do your thing, and you return a goal response reject, and the client that called this action server will have to say, oh, well, they don't want to do my thing. Otherwise, you can return an action goal response accept and execute. And so if we return that, we're saying, yeah, we'll do your thing. The next function here is handle cancel. So all we're doing is we get a handle. And basically, if the client at any point says, hey, don't do that thing that I wanted, you basically say accept, and that's about it. And we just say that we got it. And I think it'll automatically stop execution. Now, we have this thing called execute. And I'll show you how this gets, I think how this gets wired up is a little bit lower in the code, but basically you get a goal handle, which is basically, that's the goal, right? You're passing it in, and you say, I'm going to execute it. We've got this little rate thing. It's basically a wait or a sleep, like if you're doing Python, like sleep. We get the goal. Here, let me do this so you can see this a little bit better. Move this guy over a little bit more. Now we create a feedback object. We'll also create this thing called a sequence. And on the sequence, so this is the sequence of numbers in the Fibonacci series. So we push back 0, we push back 1, which are always the first two. And our result, which is the thing we're finally going to return. And what happens here? So we basically go about doing the Fibonacci sequence here as long as I is less than the goal, the order. And this is the important one here. Okay, which we're saying as long as ROS is running too, because ROS might fail and it might say like, I want to take all these things down now. I'm not going to wait for you to finish. So you want to make sure you check that in your loop. So we check as long as somebody's not canceling. If they do cancel, we basically give them the current status, say canceled, and return. Otherwise, we do the Fibonacci stuff. We publish the feedback. So this call just says like, here's the goal handle, publish the feedback, type feedback, and we wait a second, and we iterate all over all this. Finally, if the goal is done, we set the results, goal handle succeed results. So we say we're finished, and we say goal succeed, and we send it over. Cool, so that's just calculating Fibonacci sequence. Pretty simple, you probably should have done it before. Okay, so now finally handle accepted. So what this is doing, I think, basically is, this is a little bit tricky. And what's going on here is, if this function gets called, we're saying handle accepted with the goal handle, which is the thing that's going to go, which basically says calculate this order Fibonacci sequence. We're going to bind it to the execute in our class and let it run and then detach. So all this is basically doing is it's wiring up between accept and execute and spinning off a new thread. So all of the, you can do, multiple people can call this action server, and every time they call, they're going to spin off a new thread, and, there can be like 20 of them running at the same time. And finally, let's go down here. All we do is, like we've seen before, init ROS, create our class, let it run until ROS says shut down. And that's it. No, don't save it. Cool. All right, so let's run this action server, and then I'll call it from the command line. I'll just show you how to do that real quick. Don't worry if you don't get it the first time. It's not a big deal. And I'll show you how to do it from code. So let's go up, and yeah, I would say if you were modifying this also, you have to rebuild, but we didn't really touch the code. We were just kind of peeking at it. So let's execute this guy. Cool, so this is running. There was no logging output at the top, so it's not really going to do anything. It's just going to sit there. So let's open up a new terminal, and I'll call it from the command line real quick so we can see what it does. So sending these things, requests through the CLI is kind of opaque in terms of the message format. It's possible, it just doesn't look all that good. So we do it is ROS2 action. So you can, I'll show you a little bit of this. You can say action list. Well, why don't we try sending it the goal? ROS2 action send goal. And I'm going to just copy this. So basically all I'm going to do is tell it where the message type is, and then I'm going to send it the message. What's going on? Action single file. Oh, that's what I'm missing. Let's go. Needs to know which action server it's sending the goal to. Okay. I think I fat fingered that. I'm just going to do this right and copy it. Oops. Interesting. Okay, that took a second, but oh, you guys want to see me. All right, now if we correctly start the right server, or the action server, instead of the service, like this. All right, should be quiet, and then we go over here and we can send it the goal, and this is what will happen. So we can see it sent a goal of order 10, and the goal was accepted with ID. So this is for the UUID there, and then you can see it just returned a response. Boom. So what we didn't get there is we didn't get to see the steps of the feedback, but we can look over here and see that it was publishing feedback. It's just that the client doesn't actually spit that out. Cool. All right, so why don't we take a look at how to go and build a client that talks to this action server. So this is reasonably straightforward. It's still kind of convoluted because you have to handle all the cases where the client or the server can say, hey, I can't handle your action right now, or whatever. But roughly the process is like check for a connection to ROS and the action server, check for the action server, send the goal, check that the goal has been accepted after it's been sent, update with the feedback information, and then receive the final results. So why don't we go take a look at roughly what that looks like. What we can do is I'm going to, this is server, so why don't we do this over here. Why don't we open this up and take a look at the member functions. There we go. All right, let's see what we got here. Oops. Well, let's go in there. So it is workspace, there's a source, examples, minimal action client, and member function. Of course, I do that again. Cool. All right, so let's see what's going around in here. And I'll follow along here. So, again, this should all look super familiar. Header files, etc. These are exact same as before. What you'll notice also, I think it's worth noting that the client and the server, or the client and the server both use basically the same header file, right? Because they're all using a shared message. We have the header file here for right here for actions, which is useful. And then the client is just basically a ROS node, is a class that's just basically a ROS node. Again, we go through and do some scope resolution just so things aren't too long. We build constructor for our action client, and this is the same as before too. We basically need a client pointer inside of the class, and we do this. We say, hey, create a client. The template type is Fibonacci. Point it to all of our base node, basically interfaces, and name it. And then what's kind of tricky right here is we set a timer. So in the constructor, we set a timer for half a second that's bound to this send goal class or function. So basically, once you call the constructor, it'll wait half a second, and then it'll call the send goal function, which is kind of cool. Anyway, so here's a function, is goal done? That's just doing some checking. And then here is our send goal, which is called right from the constructor. And cancel the timer, say that we're not done. Check that our client is initialized. And then all this code right here is pretty simple. We look at the client interface and say, hey, check that our action server is up and running, and if it's not, spit out some messages saying so. Once the server is actually spun up, we create a goal. In this case, we're saying, hey, let's do order 10. We say send goal. So this is the tricky part right here. So this is we say, hey, we're an action client of this type, and we're sending goal, and what we have to tell the underlying action interface is basically the set of functions that we want called back for particular events within the life cycle of our action client, which is to say we want to be called back when the action client, when the goal is accepted, when it gets feedback, and then when there's finally results. So we need callbacks for all three of those. And we can see that here. Basically, we bind the the goal response, the feedback call, and the result call. And then we send them all off as this asynchronous message, or asynchronously send the goal, which should kick it off, and then we just sort of wait for the callbacks to happen. So let's go look at those callback functions. First thing here, we have a couple private member variables. And first one is goal response callback. So this is going to happen whenever let me move this forward a little bit. Send goal. So this is going to happen as soon as the action server itself says, hey, I got your request and I'm going to handle it. Because it can say, hey, the server, I can't do this, I'm busy, something's happened, I can't handle your request. But more often than not, it'll say yes. So here's the callback. What we do is we get the goal handle, and we can tell, whether it was rejected. If it's not, in either case, we just basically print things out, and that's about it. And then we come down here, and this is basically our feedback callback, and we get the feedback information, and we just print it out. Pretty straightforward. And then finally, the results. We have this wrapped result thing, and the wrapped result is basically because there's the output, right, which is the sequence of numbers 0, 1, 2, or 0, 1, 1, 2, blah, 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 blah. But then there's also a status code, and the status code will tell you whether the action itself succeeded, was aborted, was canceled, etc., etc., etc. So first we check that result code, and we basically log whatever happened. If it succeeded, we just drop out of this switch statement. And then we go through and print all the results. And then finally, we just have this exact same main pattern that we've seen before multiple times, where we just instantiate our thing, basically spin indefinitely or until our goal is done, and then we shut down. So I guess it is a little bit different in the sense that we wait until the goal is done and then we just shut down afterwards. It doesn't run until ROS shuts down. All right. So why don't let me exit out of here, and no, we won't save that. We'll give this a run. So the quick way you do this is to run, and now, so I believe our server is still running. So all we have to do is run our client code like this. Oops. And we should get something interesting. Sending goal accepted by server, waiting for result. And you can see we're getting the next number in the sequence. And finally, we get the full result. And if we toggle over here, we should be able to see, yep, same set of things as before. Okay. So, you've just seen the set of API primitives upon which most ROS-based systems are made. Generally speaking, when you build a robot, you're going to work from simple to complex. So you're going to start with the nodes, the publishers, the subscribers, etc., etc., and then you're going to take those, build up smaller services, and from those services and other things build up actions. So generally you work in that process. It's worth noting that we didn't cover quite everything. I think I've mentioned that multiple times. And then also for all of this stuff, there is also Python API. I would generally recommend that if you're trying to learn and just get the basics down, sometimes working with the Python API can be a lot easier and a little bit more forgiving. So that might help, especially if you're stuck on one subject. It doesn't hurt to try it in Python and then see if you can get it working in C++. Oh, I guess the other thing worth noting is there's a ton of other examples inside of this workspace, so feel free to paw around and see what you can get running and seeing what you can change. I think it would be super, super helpful for next time. All right. All right, so I hopefully that was a pretty good introduction to the ROS2 dashing API. I think we got most of the bases covered: nodes, subscribers, publishers, services, and actions. And those primitives basically make up most of your ROS system in terms of software. There's still a lot of other functionality, a lot of other tools out there, but that handles most of the internal software architecture. So next time we'll be covering the ROS2 command line interface. So I'll show you all of the command line tools for starting, stopping, looking at, introspecting, and capturing ROS2 data and ROS2 messages, and that should be a lot of fun. So, hopefully see you next week.